everybody, this is Dr. Bricker here with a video for the remaining parts of Chapter 28. So I just wanted to tie up some loose ends with the photoelectric effect and then go on to the rest of the chapter. So I thought we could start with this example problem. What are the threshold frequencies and wavelengths for electron emission from sodium and from aluminum? So this is the photoelectric effect. We can look up the work function of both of these materials in table 28.1. So you see here, this is called the work function. For sodium, it's 2.75. For aluminum, it's harder to remove electrons from aluminum, work function 4.28. Okay, so let's take a look at this. So the cutoff frequency, this is the minimum frequency that you need in order to liberate electrons. You can use equation 28.5 and use the version of H, Planck's constant, in electron volt seconds. So when you do that, put in the work function, put in H, you get this frequency for sodium, and you get this frequency for aluminum. So aluminum, higher frequency photons required. That means more energy. Higher frequency means more energy. Okay, so then you can figure out, as is being done here, the cutoff frequency, the minimum frequency that you need to liberate these. Then if you want to get the wavelength, we could use this relationship for the wavelength. So the wavelength is the speed of light, that's what C is, the speed of light, 3 times 10 to the 8th meters per second, divided by the frequency, which we just got from up here to get the wavelengths. Okay, good. So sodium, 452 nanometers, aluminum, 290 nanometers. Again, remember, lower wavelength means higher energy, so that works out as well. Okay. So the photoelectric effect can be observed with sodium for less than 452. This includes blue and violet in the spectrum, but not red, orange, yellow, or green. So you have to have high enough frequency to be able to do this. Aluminum, on the other hand, needs ultraviolet wavelength, so no visible light will work for this. This is ultraviolet, beyond the visible spectrum. Okay, great. Here's another example. What are the minimum electron speed and stopping potential if sodium is illuminated by a wavelength of 300 nanometers? Okay, so let's go back up to this. Cutoff wavelength for sodium 452. So here we have a wavelength of 300. So this is even more energy. The previous problem, we just figured out how much to just liberate an electron. In this part, not only are we liberating an electron, we are giving it extra energy. Okay, so whatever's left over after the work function goes into kinetic energy. So the kinetic energy of emitted electrons and the potential difference necessary to stop them depend on the energy of the incoming photon, so H times F, and the work function. So whatever is left over, again, after the work function goes into the kinetic energy. And it says, you know, what's the maximum electron speed? Well, we can figure out the kinetic energy and then use what we learned in physics 220 to figure out how fast the electron will be moving. Okay, so here's the formula. Maximum kinetic energy, HF, this is the energy that the photon has, minus the work function. Okay, so the amount of energy that the photon has turns out to be 4.14 eV. Okay, you can get that by using Planck's constant times the frequency. Just be careful of the units. Okay, so we're using the version of H that is electron volt seconds, and then multiply it by the frequency, which is 1 over seconds, and you're left with eV here. Okay, so you get 1.39 eV. That's how much energy is left over that goes into kinetic energy. And then you can convert it to joules. Remember, 1.6 to the minus 19th joules is 1 eV. We need the kinetic energy to be in joules to be able to figure out the speed, because now we're back into looking at SI units. Okay, so again, from physics 220, kinetic energy 1/2 mv squared. The m here is the electron's mass, 9.11 to the minus 31st kilograms. So then you can take this formula, solve for v. So 2 times the kinetic energy divided by the mass, take the square root of that, will give you the speed. So you can see why the kinetic energy has to be in joules. The mass here is in kilograms, so to make the units work out. You can't leave the energy in electron volts. You won't get the units to work out to meters per second, as it says down here. Okay, good. So what's the stopping potential? Here's the formula for the stopping potential. Remember what the stopping potential is. You take the battery in the photoelectric effect setup and you reverse it. You want to stop all electrons from making it across. So you're taking all of the kinetic energy from electrons and turning it into electrical potential energy. That's where this formula comes from. Okay, so you had the maximum kinetic energy divided by the charge of an electron. Now, going back here, if you leave the kinetic energy in electron volts, so leave the kinetic energy in electron volts divided by E, you just get volts. That's the nice thing about the unit of electron volts. If you use that set of units and the energy is in EV, if you just divide it by E, it comes out into volts. If you're not comfortable with that, just keep it in joules. Use the charge as 1.6 to the minus 19 coulombs, and you'll get the same exact answer. Okay, so that will stop all electrons from making it across. Okay, good. As you can see, that's a synopsis of what I said here. Okay, good. So photons, we've talked about photons, started talking about it with the end of chapter 25. What are they? Depending on what we're interacting with, you can think of light as being little massless particles that are moving. So if you go back to the double slit experiment, but use a much dimmer light intensity, the fringes will become too faint to see. So this is, after you've run this experiment for a long time, this is more typical what it would look like. But if you just do this for a small bit, instead of the picture being kind of faded out, you can see individual spots where the electrons were landing. Okay, so this is an example of light behaving as a particle. Okay, all the way from A through D. So individual photons pass through double slit, and as the image builds up, the photons are grouped into bands at exactly the positions that you would expect for the double slit experiment if you thought about it as waves. So you see particle-like dots forming these wave-like fringes. So remember back in chapter 17, double slit experiment, we just had a nice picture like this. We thought of it as waves. But if you take the intensity down, it actually kind of appears, especially in these earlier ones, as particles hitting. So if only one photon is passing through the apparatus at a time, it has to somehow interfere with itself, or why would you get this pattern, this wave-like behavior? So it's kind of both things happening at the same time, wave-like and particle-like behavior happening at the same time. So sometimes light exhibits particle-like behavior, sometimes wave-like behavior. Again, mostly it depends on the energy that the photon has, and that corresponds to the wavelength, and what the photon's interacting with. Okay, so the photon nature of light isn't apparent in most cases. With the double slit experiment, like the lab that you did, or actually that was a diffraction grating, same idea though, it just appeared nice and bright from the beginning. The particle nature didn't come out in that lab. It would if the intensity was really, really small. Okay, so here's an example. We have a 1 milliwatt, so remember what a watt is, a joule per second, energy per time. A laser beam, a light beam from a laser pointer. Here's the wavelength, 670 nanometers. Okay, so as soon as you know the wavelength, you can calculate the energy. Okay, if we need to know that. How many photons strike the screen per second? Okay, so we've got 1 milliwatt, which is 1 to the minus third, and a watt is a joule per second. So each second, you get 1 times 10 to the minus third energy hitting the screen. And you know, each photon has a certain amount of energy given depending on the wavelength. This is the total amount of energy. How many photons do we need to add up to 1 to the minus third joules? That's the idea here. Okay, so here's a way of doing it. The frequency you can figure out from the wavelength, It turns out to be 4.48 to the 14th hertz. So you can figure out the energy then. H times F. Here's Planck's constant, 6.63 to the minus 34th joules times seconds. Multiply it by F, 4.48, oops, that should be times 10 to the 14th hertz. And then hertz is a 1 over seconds, so we're left with joules. So each photon has this amount of energy. But we know we need to have a total of 1 to the minus third. So if you take the total energy, divide it by how much each photon has, you get the amount of photons. So each second, 3.4 times 10 to the 15th photons hit the screen. So each photon has a small amount of energy, so you need a whole bunch of them to add up to 1 to the minus third joules every second. Okay, good. So just be careful with the units. So early light detectors consisted of polished metal plates in a vacuum tube. So when light fell on the plate, an electron current was generated. So you shine light on metal, electrons are freed, and free electrons, you can guide them with an electric field, and that makes up current, moving charge. So you can detect light happening that way. Okay. A solar cell works much like a battery, but the energy to lift charges from a lower potential to a higher potential come from photons. So photons come in, hit the metal, electrons are freed, they go from a lower potential to a higher potential, and you can power this little fan that way. Okay? So we're using photons from the sun, hitting something, freeing electrons that consists of current, and then that current is used to power. In this case, it looks like a little fan. Okay? Good. Here's another example. 1 watt monochromatic light, so that means just one wavelength, 550 nanometers. Okay, so 1 watt or 1 joule per second, don't forget what a watt is. Each photon has this wavelength, 550 nanometers. Illuminates a silicon solar cell, driving a current in a circuit. What's the maximum possible current this light could produce? So this is under perfect conditions. What's the maximum current? Okay, so let's take a look at this. Okay, so the wavelength is shorter than this 1200 nanometers threshold wavelength. So shorter wavelength means more energy, so we're well within that range. So the photons will have sufficient energy to cause charge carriers to flow. So remember how this works. Each photon of light can give its energy to one charge carrier. So each photon that comes in can free one electron. And then, the electrons, that's the charge carrier. That's how current is built. If you remember back from the current chapter, voltage current chapter, you have electrons moving. That's what current actually is, the amount of coulombs per second. That's what an amp is. So the maximum number of charge carriers that can possibly flow in each second is equal to the number of photons that arrive each second. Okay, and then each of the freed electrons, we know the amount of current they have. Okay, so if we can take the amount of photons coming in, that's the same as the number of electrons that are freed. The charge on one of them is 1.6 to the minus 19th coulombs, and that's happening every second. Okay, so we need to know how many photons we have coming in, because that's the same as the number of electrons freed. Okay, so then it becomes similar to the last problem that we looked at. So 1 watt is 1 joule per second. The frequency is given, the wavelength is given, so we could calculate the frequency from this formula. Take the speed of light, divide it by the wavelength, you get 5.45 to the 14th hertz. Okay, so then each individual photon has this much energy. Okay, so then to get a number of photons that you have arriving per second, this again really similar to the last problem, you've got 1 joule per second. That's the total amount of energy per second. Divided by the energy for 1 photon, you get this many photons, 2.7 to the 18th photons. So that's how many electrons we could possibly have freed. Okay, so 2.77 to the 18th electrons per second. Multiply it by the amount of charge for 1 electron. That's what's happening here. Total electrons per second. Multiply it by the charge per electron. That's what you have here. And you get the total charge. And this is happening every second. So coulombs per second, this is the current. So 0.44 amps. So that's what the sun is giving us. And that's like maximum efficiency. So the key concept underlying the solution here is that one photon gives its energy to one electron. That one electron is freed. It's a charged particle. It moves, and that's where the current comes from. Okay, real solar cells less than this because some photons are reflected. Some will not transfer their energy, that sort of thing. So this is ideal conditions. That's the best you could hope for. So detecting photons, you probably have done this with your phone. Charge-coupled devices, the CCD cameras, or CMOS detector is a digital camera that consists of millions of pixels. They're just waiting to free electrons, basically. It's metal or a semiconductor device, waiting for photons to come in, and in doing so, we can free an electron. If the frequency exceeds the threshold frequency, a photon hitting a pixel liberates one electron. The electrons are stored inside the pixel. The total charge is proportional to the light intensity. So the more and more come in, the more and more electrons are freed and stored. The more you have in a certain pixel, the more intense the light would be. Okay? And this happens over and over again. So photodetectors based on silicon can be triggered by photons as low as 1.1 eV. So this is in the infrared. The light sensing chip in your camera can detect infrared signals given off by a remote control. So if you press the button on a remote control, aim it at your camera, take a picture, you'll clearly see the infrared emitted by the remote. You can't see it with your eyes, but your camera can do it. It can pick up infrared sometimes. Okay, good. So pretty cool. Here's an example problem. Exposure to ultraviolet light can damage the skin. So this is light with more energy than just visible light. For this reason, there are suggested limits for exposure to ultraviolet light in work settings. And the limits are wavelength dependent because the wavelength corresponds to the energy. At a wavelength of 313 nanometers, the maximum suggested total exposure is 500 millijoules per square centimeter. For 280 nanometers, okay, so this is a smaller wavelength, that means it's higher energy. The limit falls to 3.4 millijoules per square centimeter. Okay, let's see. What is the photon energy corresponding to each of these wavelengths, and how many total photons do each of these exposures correspond to? Okay, so let me just do it for the one case, the 313 nanometers. I just wanted to show you another way of doing this. So remember in class I told you could use HC is equal to 1240 EV times nanometers. This is just a shortcut. And then the energy is, this is the total energy up here. The energy is HC divided by the wavelength. It's also H times F, but it's HC divided by the wavelength because the frequency is the speed of light divided by the wavelength. So if you are comfortable with this, H times C, that thing I've already multiplied together, and this is an EV, is 1240 EV nanometers. That is H times C. And then if you just divide it by the wavelength, 313 nanometers, the nanometers actually cancels out, and then you can figure out what the energy is. Okay, so I can take 1240, 1, 2, 4, 0, divided by 313 and get the answer, the energy in EV. So about 3.96. I'll just put 4 EV. That's the energy that one of them has. Now that's not an SI unit, it's a perfectly good unit, it's just not an SI unit. Then I can convert that to joules if I want to. So 4 EV, and I know the conversion factor, 1 EV, 1.6 to the minus 19th in joules. So this would turn out to be, let's see, 6.4 looks like, to the minus 19th joules. Check my math, but I think that's okay. 3.2, 6.4. Yeah, so that's the energy that one photon has. Not a lot, but there's going to be a lot of photons, though. That's the first part. The second part is how many photons do we have? Well, if you have a total energy of 500 millijoules, this is the total energy, 500 to the minus third, and then we know the energy for 1, 6.4 to the minus 19th joules. That's for 1 photon. This is per photon. You can figure out the total amount of photons. This is J here. Okay. So the joules cancel out and you're just left with the amount of photons that you have. So it's a lot. Okay, so I'll leave that part of plugging it into you, but this is the way to do the second part. And that's per square centimeter. Okay, and then the other parts are the same way. Okay, let's get back to the notes. Okay, here's another example. Port wine birthmarks can be removed by exposure to 585 nanometer laser light. Okay, good. So that's the wavelength. You can easily calculate the energy. I say easily because there's just a constant that relates the energy to the wavelength. So if you know the wavelength or the frequency, you can really quickly calculate the energy. Pulses are strongly absorbed by oxyhemoglobin in the capillaries in the birthmark, destroying them. A typical laser pulse lasts for 1.5 milliseconds, so 1.5 to the minus third, and contains an energy of 7 joules. What is the power of the pulse? Okay, so the power is the energy, in this case 7 joules, divided by the amount of time, 1.5 to the minus third seconds. So you can get the power that way. Okay? How many photons are in each pulse? Okay. So you can figure out the energy of 1 photon. Right, here's the wavelength of 1 photon. You can figure out the energy that 1 photon has. And then once you have the energy of 1 photon, you can figure out how many of them do you need to add up to 7 joules, just like we did before. So for part B, the energy, however you want to do it, you can take the wavelength here and calculate the frequency, or if you want, you could use Hc divided by the wavelength, just like we did. Get the energy in electron volts. So this would be 1240 eV nanometers divided by 585 nanometers. Okay, this would give you the energy in electron volts. Convert it to joules. That's the energy for 1 photon. Divide 7 by the energy. This is what I mean by 7. Divide the 7 joules by the energy for 1 to get the total amount. So this part is similar to what we just did in the last couple of problems, actually. Okay, so lots of work with photons in this chapter. The next thing we have is our matter waves. So de Broglie, that's how you pronounce this, de Broglie here, de Broglie, reasoned by analogy with Einstein's E is equal to hf for a photon, and with some ideas from his theory of relativity that all material particles should have some wave-like nature. Okay, so light, which usually you think about as a wave, can behave like a particle under certain circumstances. So de Broglie's idea was, well, maybe actual particles can sometimes behave like waves. And it turns out he was right. So de Broglie determined that if material had momentum, m times v, that's from physics 220, then its wavelength must be given by this. So anything that has mass and a speed has a wavelength. I have a wavelength, a basketball shot has a wavelength. It just depends on the mass and the speed. So this is called the de Broglie wavelength. Planck's constant divided by the momentum, or Planck's constant divided by mv if you put this in. Okay? So sometimes it's written like this. The momentum is equal to h divided by the wavelength. It's also equal to, the momentum is actually also equal to m times v. Okay? So you can get it several different ways. Okay, so we all have our own associated wavelength. You'll see that our wavelength, why don't we see our wave-like behavior come out? We're not able to squeeze into these little holes in our regular life, and we'll see that in some examples. We have a wavelength, but our wavelength is really small, so we're never going to be physically going through anything that small. So our own personal wavelength doesn't really isn't exemplified. Here's an example. What is the de Broglie wavelength of an electron with a kinetic energy of 1 eV? Okay, so electrons are small. Sometimes wave-like behavior of electrons actually does come out. If you shoot an electron through a really small hole, you will see that it will behave like a wave. So if you shoot an electron through a small hole, let me give you an example. Take an electron, you shoot it through a small hole, you would think that it would just land on the screen here. But it doesn't. You actually get some here, some here, some here, etc. Just like you would from the single slit experiment. So in that case, the electron's wave-like behavior actually does come out. It's small enough that it can go through small openings. Okay, anyway, back to this problem. What is the de Broglie wavelength of an electron? Okay, so you know the mass of an electron with kinetic energy of 1 eV. Okay, so we can figure out how fast an electron is moving. So this kinetic energy is good, 1 eV, but you need to put it into joules, as is being done here. 1 eV is 1.6 to the minus 19th. So if you take this formula, kinetic energy is 1/2 mv squared. Solve for v, so multiply both sides by 2, divide by m, take the square root. You get this for the speed. Okay, and then we could use our new de Broglie wavelength formula to figure out the wavelength of this particle. So h divided by mv, so h, this is just Planck's constant. Use the mass of an electron and the speed that you just figured out, you get 1.2 to the minus 9th, or 1.2 nanometers. Although fast by macroscopic standards, electron gains the speed by accelerating through a potential difference of just 1 volt. So take an electron, go through 1 volt, it'll get 1 eV of energy. We just saw how fast it's going to be moving. Here's its associated wavelength. So electron's wavelength is small, but it's similar to the wavelength of X-rays and larger than the 1.1 nanometer spacing in crystal. We can observe X-ray diffraction. If an electron has a wavelength, has a wave nature, it should be observable, and it actually is. This works out. I gave you the example of going through a single slit. You would see the diffraction pattern. And you do in real life. It works. Electrons don't just go through the hole and end up on the other side. They end up spaced apart. There's a distribution of where they actually land. So yeah, it looks just like this. So matter waves exhibit all the properties associated with waves. It's just that you have to be able to go through small openings. Electrons can do that. So here's an example of electrons behaving like waves. Okay, so this is not light going through a single or 2 slits. This is electrons going through. Okay, and not just landing right across, they're landing on a screen spaced out like this. The reason you don't see macroscopic objects like baseballs or people behaving like waves is because of their wavelength. My wavelength is not going to be anything near a small opening to squeeze through for that interference diffraction idea to come out. But I do have a wavelength associated with myself. Okay. Here's an example. Calculating the de Broglie wavelength of a smoke particle. One of the smallest macroscopic particles we could imagine using for an experiment would be a very small smoke or soot particle. They're about 1 micrometer, so 1 to the minus 6th meters in diameter. Too small to see with the naked eye and just barely at the limits of a microscope. The mass of this particle is really small, also 10 to the minus 18th kilograms. And we could estimate the de Broglie wavelength for this 1 micrometer diameter particle moving at a speed of 1 millimeter per second. Okay, so we have the speed, we have the mass, h is just a constant, we can figure out the wavelength associated with this particle. Okay, so here's the momentum, m times v, something like about 10 to the minus 21 kilogram meters per second. So here's the wavelength. Put all that together, the wavelength is really small. The wavelength is much smaller than the particle itself, much smaller than the size of an individual atom. We don't expect to see this particle exhibiting much wave-like behavior. Okay, it just doesn't come out. The opening that it would go through, it wouldn't. You wouldn't have anything to that size. Okay, cool. Energy is quantized. That's the next part here. It kind of we got a taste for that when we talked about the photoelectric effect. We learned that waves on a string fixed at both ends form standing waves. Is there a standing matter wave? So think back to physics 220. We did standing waves. You know, things like waves could only exist at certain modes. Like this was mode 1. Here's another one. This was mode 2. We did some nice experiments with that. Actually made these waves in the lab. Are there matter standing waves? It turns out there are. So if you take a particle and you put it in a box, it has an associated wavelength. So everything has a wavelength. Now this wavelength has to be able to fit in this box, right? These are the only wavelengths that existed from physics 220. The wavelength that you have also has to fit into this box. Okay, since particles have wave-like properties, we consider a wave reflecting back and forth from the end of the box, and then you get standing waves, just like we did in physics 220. I think it was probably chapter 16 or so. For a wave on a string, we saw that there were only certain possible modes, as I outlined here before. The wavelengths we saw were 2L divided by N. And the N could be any multiple, 1, 2, 3, 4, etc. So when N was 1, that was the fundamental frequency, and then we had higher frequencies or wavelengths in this case. Okay, so if this is what the wavelength is really confined to be, it's got to be something like that. But we also know that the wavelength has to be Planck's constant divided by the momentum. You can take both of those ideas and put them together, and you can figure out the size of the box that the wave-like nature has to be confined to. So H over P is 2L over N. You put both of those wavelengths together. Like I said, this one equal to that one. Okay, so for the node of a standing wave of a particle in a box, you can solve for the momentum then. So there's only discrete values of the momentum, right? It could be when n is equal to 1, you get a certain momentum. N is equal to 2, you get a certain momentum. There's nothing in between. There's no n is equal to 1.5 or n is equal to 2.37 or anything like that. This has got to be integer multiples to actually have these standing waves. Okay, so when you see quantum mechanics and quantize, that's where the name comes from. Only discrete values, not a continuous spectrum, just discrete values. Okay, the energy of the particle, we can figure that out too. There's only discrete values for that. So 1/2 mv squared. Now remember, you can write the momentum as m times v. So using that idea, you can go from this equation to that equation. So from this one to that one. Put in the momentum is m times v, and you get this relationship. The energy is therefore restricted to certain values. So the energy is quantized. It only can have certain values. So the momentum is given by this equation. The energy is given by this equation. So this is a particle in a box. Okay, so you can't just have any old energy. There's only certain values. You put it all together and you get this for the energy. Okay, so again, n is just an index. 1, 2, 3, 4, etc. M is the mass of the particle in kilograms. H is Planck's constant. All of this will give you the answer in joules. Use H, 6.63 to the minus 34th joule seconds. Okay. Because the wave nature of matter, a confined particle only has, again, certain energies, just quantum steps. Okay. N is called and we'll see this later, the principal quantum number. Okay, so it characterizes the energy that the particle can have. Okay, so when n is equal to 1, this is what you have. You just put 1 in for n, you get this. So all the multiples of this are just multiples of the ground state energy. So E is equal to 1 is called the ground state energy. Okay, good. Excellent. So again, multiples of the ground state. E1, and then 4 times as big, 9 times as big, 16 times as big when you put in n and square it. Okay. So an atom is more complicated than a simple one-dimensional box, but sometimes you've got to start somewhere when you talk about a model. And you could think about the electron confined to the atom. So in a sense, it's confined to a box. So electron orbits are in some cases standing waves, and the energy must be quantized, so you can only have certain energies. Later on, you might think about chemistry. You could have only certain orbits. It's the same idea here. You can only have certain, how many shells are filled when the n is equal to 1 state, that sort of thing. It all comes from this. Okay, so let's look at this example. An electron is confined to a region of space of length 0.19 nanometers. This is comparable to the size of an atom. Not the size of a nucleus, the size of an atom. What are the first 3 allowed energies of the electron? So you can model this as a particle in the box, and you get pretty good results, actually. It gets more complicated when you get more complex atoms, but like for a hydrogen atom, this works out pretty well. So the ground state, using the mass of an electron, that's what we have here. N is equal to 1. You get 1.7 to the minus 18th, or 10 eV. The next highest energy, 40 eV. When you put in 2 squared is 4. Put in 3 squared is 9. So these are the multiples of this. Okay, and those are the only allowed energies. These energies are significant. E1 is larger than the work function of any metal. So confining an electron to a region of the size of an atom limits its energy to states separated by significant differences of energy. Clearly, our treatment of electrons and atoms must be a quantum treatment. Okay, and we'll see that in this chapter and the following chapter. Okay, good. Energy jumps and quantum jumps, quantum leaps maybe. So 1925, Schrodinger, maybe you've heard of Schrodinger's cat before, developed the first complete theory of quantum physics called quantum mechanics. Okay, so he didn't develop a theory of why this works. He just developed a theory of how it works. Nobody really knows exactly why this is going on, but there's a machinery in place, mathematical machinery in place that describes this. Okay, so this is coming on about 100 years since this happened. It describes how to calculate quantized energy levels of a system of particles in a box to electrons and atoms. Okay, and then we could also see how to describe energy losses or energy gains. Electrons going up in energy, dropping down in energy. Turns out it's from either absorbing a photon, you go up, emit a photon, drop down in energy. So this is an energy diagram. Useful way of visualizing what's going on. So ground state, that's when n is equal to 1. This is from our previous example. These are the excited states. Electrons can only have multiples of energy. We calculated n is equal to 1, 2, and 3, but when n is equal to 4, you get 4 squared, or 16 times the ground state energy. Okay, so this is a particle, an electron, in a 0.19 nanometer long box. Okay, so excited states are levels above the ground state. Okay, so you can see how the energy goes up as you climb the ladder here. The lowest rung is called the ground state. Higher levels are called excited states. So if a quantum system changes from one to another, its energy changes. So the way that it can change, you can only go from one to another. You don't have to. You can skip one. You can go from, say, 2 to 1 or from 3 to 1, but you can't go from 4 to 3.5. There's no such thing as 3.5. Okay? Or you can go from 1 to 2, or you can go from 1 to 3, or you can go from 2 to 4. Any way up or any way down. You could skip rungs, if you will, on the way, but you have to land on a rung. Okay? So if you go from 1 up to 2, you could figure out the amount of energy associated with that. Actually, this is going from 2 to 1. So the difference in energy would be 30 eV. This energy was 40, this was 10, so the difference is 30. So a transition from 2 to 1 requires the emission of a 30 eV photon. So if you go from here to here, you emit a photon of 30 eV. to go from 1 up to 2, you have to absorb a photon of 30 eV. It works in reverse as well. So this is the magnitude of the difference in energy. So where you end up minus where you began. So you ended up at 1, which was 10. You started at 2, which was 40. The difference is 30. So that's the energy of the photon that's emitted. And we also know then you can calculate the frequency of the photon that's emitted. This just comes from what we did before. The frequency is the difference in energy then divided by Planck's constant. Okay? Excellent. So if you absorb a photon, you can go in the other direction. So here we're going from 1 to 3. The difference is 80 eV. You have to absorb an 80 eV photon to do that, to jump up. Okay? And if you want to, then you can figure out the frequency of the photon that you absorbed. So it works going up or going down. Just remember, going up you have to absorb, going down you have to emit. Okay? Excellent. So this is kind of a synopsis of what I've said here. The photons from the emission spectrum, the photons form the emission spectrum. So different molecules and atoms have different emission spectrums. They're built differently. So if you take spectrometer and you look at fluorescent light, you'll see a specific signature. It just depends on what the fluorescent light is made out of. Okay? So hydrogen has its own spectrum, helium has its own spectrum, so sodium has its own spectrum, its own signature. All these different quantum emissions taking place. So here's a little summary of quantum physics and what it has to say about atomic levels. Energies are quantized. You can only have certain values. There's nothing in between. So that goes against our understanding of our macroscopic world. You could say you're going into the tech building, you could walk up the nice sidewalk, without steps. I guess it's called a ramp, actually. You could walk up the ramp, you could be anywhere you want to on the ramp, or you could take the steps. Now, if you take the steps, you can only be at certain levels as you go up. That's quantum mechanics. Going up the ramp, that's our macroscopic world. The other thing to get out of this, the ground state is stable, so the ground state is where you want to be, and we have transitions up from there and then back down to there. Okay, and quantum systems emit and absorb a discrete spectrum of light. So there's nothing left over. If you want to go from 1 to 2, you have to absorb a specific energy photon. If not, nothing will happen. Same thing on the way down. So if you go from 40 eV to 30 eV, you're emitting 1 photon of 30 eV, not 2 photons of 15 or anything like that. Okay, here's an example. An electron in a quantum system has the following allowed energies: 1 eV, 4 eV, 6 eV. What wavelengths are observed in the emission spectrum? Okay, so first of all, what possible transitions do we have? Well, you can go from 2 to 1, you can go from 3 to 1, but you can also go from 3 to 2. So there's 3 different possible transitions going on. So it would be something like this. Let me see if there's a better picture. Oh, there's a better picture. So you can go from, oh, excellent. You can go from 3 to 2. That's the first one here. You can go from 3 all the way to 1. That's this one. Or you can go from 2 all the way to 1. And we can figure out those differences in energy. From 3 to 2, that would be 2 eV. From 3 to 1, that would be 5 eV. That's the difference in energy. And then from 4 to 1, the difference is 3. Okay, so we've got those differences in energy. We can calculate, let's see, what do we want to calculate actually? What are the wavelengths? You can calculate the wavelengths associated with those. Okay, so there's the energy differences that I mentioned. And then you can calculate what's being done here is, like we did before, figuring out the wavelength from the frequency. Okay. If you want to, you could use this. Difference in energy is hc over the wavelength. So then the wavelength would be hc divided by the difference in energy. Okay, so let me just do the first one. This would be 1240 eV nanometers, and then let's say we're going from 3 down to 2. The difference in energy would be 2 eV, so then you get 620 nanometers. It's a little cleaner maybe than this. That's this one here I just did. My little method here, you don't have to keep multiplying. You don't have to keep worrying about H and C, multiplying them together. If we want the wavelength anyway, why not just do it like this? It saves the time of getting the frequency, and then once you have the frequency, calculating the wavelength. So this is kind of takes out that middle step. Okay, good, and you could do it in your head. Okay, great. So transitions with small energy difference correspond to lower energies, larger wavelengths, and bigger transitions give you a higher frequency, lower wavelength. Okay, we also have the uncertainty principle. This is another consequence really of this quantum mechanical world where weird things happen, to put it mildly. So for a particle such as an electron, if you know where it is, you cannot know exactly how fast it's moving. That's different for us. We know where we are, we know how fast we're moving, especially say you're in your car or something. Counterintuitive notion is a result of the wave nature of matter. So you can design an experiment in which electrons moving along the y-axis pass through a slit of width A. Okay? So this is the single slit problem that we did. The slit causes the electrons to spread out and produce a diffraction pattern. This really is because they have wave-like behavior. Their wavelength is on the order of this opening, so wave-like behavior comes through. Okay, this is just like we did in chapter 17. Okay, these are actual particles. You would think that it would just land right on the screen right across, right? You would think that they would all land right here, but because they have a wave-like behavior that's being brought out from the size of the opening, they act, the wave-like characteristics come out, and you actually see electrons land here, you see some land here, etc. Most of them still land in the middle, but then you get this diffraction pattern. Okay? So what's going on? I mean, why are they just not all landing across? That's where the uncertainty principle comes into play. So same thing we had before. The slit opening is size A, the aperture size. They come in with speed v. They have x part of the velocity. They must, right? If they are not going straight across, there must be some component of the velocity this way for them to actually not just all land in the center. Okay, so you can think of the experiment in a different way, as making a measurement of the position of the electrons. As an electron goes through the slit, we know something about its horizontal position. So we're thinking that it doesn't have a horizontal velocity, but there must be some horizontal velocity, or why would it end up not just all in the center? So you can establish an uncertainty in where it's located. That's the actual aperture size. After passing through the slit, the electron strikes the screen, not right straight down at different places. So there must be a horizontal component to the velocity. By forcing them through the slit, we gain knowledge about their position. So you put them through the slit. Okay, now you kind of know where they're at. They're within the aperture as you're sending them right through. You don't know exactly where. You just know somewhere in the aperture, so delta x. So by doing that, we introduce the uncertainty and the speed. So they must not just all be going straight through. There must be some uncertainty in the velocity of the horizontal direction, as you can see from this picture here. Suppose we narrow the slit in the experiment, allowing us to determine the electron's horizontal position more precisely. So you make the slit smaller and smaller, but remember what happens to the single slit when you make the opening smaller and smaller. It spreads out more and more, so you get more of an uncertainty in the velocity then. Just like we did with actual waves, send them through a slit, you make A smaller, you make the width larger, this direction. So by making delta x smaller, you make delta v bigger. And this is a synopsis of what I've said there. So improving your knowledge of the position decreases your knowledge of the velocity. So this is really what the uncertainty principle is. And it turns out, here's what you have. Uncertainty in position times the uncertainty in the momentum. This does not mean the change in x or the change in p. This means uncertainty in x, just like we did in lab. And then delta p x is the uncertainty in the position. This has to be greater than or equal to h, Planck's constant, divided by 4 pi. Okay, so without deriving it, just sort of thinking about it, you need calculus to come up with this. You get this equation, and this is called the uncertainty principle from Heisenberg. Okay. So no matter how good your experiment, you cannot measure both x and p simultaneously with good precision. There's always some uncertainty in that. Make one smaller, you make the other one bigger. Okay, this is because the wave-like nature of matter is coming out. Okay, here's an example we can take a look at. What range of velocities might an electron have if confined to a 0.3 nanometer wide region, the size of an atom? Okay, so we're confined to that region. We don't know exactly where we're at. This is delta x, the uncertainty in position. They're saying how much, let's see, what range of velocities. Okay, so we can figure out the uncertainty in the momentum, and the uncertainty in momentum is mass times the uncertainty in the speed. And then part B, 1 micrometer diameter dust particle, mass is given, confined to a 5 micrometer long box. Can we know with certainty if the particle is at rest? If not, within what range is its velocity? So it's confined to this 5 micrometer box, so you're making delta x 5 micrometers. So you know the uncertainty in the position is something like this. There's a corresponding uncertainty in its velocity. So when it says what is this range of velocities, they're saying what is the uncertainty in the velocity. So you can't know for certain where it's at, or what its speed is, rather. Okay, good. So synopsis of what I've said. So we aren't given the exact position, but we know it's within 0.3 nanometers. This means that we have specified the electron's position within 3 to the minus 10th meters. That's what 0.3 nanometers is. So then you can solve for the uncertainty and the momentum from the uncertainty principle. And don't forget, the uncertainty and momentum is mass times the uncertainty and speed. Okay, so then once you get the uncertainty and momentum from this equation, you can get the uncertainty and speed. That's where this is coming from. Okay. I should say velocity, not speed. Okay, so if you confine it to that space, you know it must have a range of velocities 2 times 10 to the 5th. Because the average velocity is 0, the particle is equally likely to be moving left or right. So the best you can say is that the electron's velocity is somewhere in this interval. That's the range, right? That if you think about this to this, that total range is 2 times 10 to the 5th. Okay? That's the best you can do. Okay, so you can't know where it is again. This is part B. You have an idea where it is. It's in the box, so the uncertainty position is 5 micrometers. Same thing that we did before. You can figure out the uncertainty and momentum from Heisenberg uncertainty principle here. Put it all together, just like you did in part A. This is the uncertainty and the speed. Not very big. I mean, it's a small number, but it's not 0. Okay, good. So this value of possible velocities will be centered on 0, like it's at rest. But there is some uncertainty because you don't know exactly where it is. Here's the range of possible speeds. All right, this should be v sub x here. Okay, good. Our uncertainty about the electron's velocity is enormous. For an electron confined to the region of this size, the best you can do is state that its speed is less than 1 million miles per hour. Okay, pretty interesting stuff. Now the dust particle, on the other hand, is a completely different story. We can't say for certain the particle is is absolutely at rest, but knowing its speed is less than this value means that the particle is at rest for all practical purposes. At this speed, the dust particle would require nearly 6 hours to travel the width of one atom, different than what the electron was. Okay. So I guess the reason that we're looking at an electron versus dust particle is for an electron. Let me go back. Whoops. The range here was 2 times 10 to the 5th meters per second. That's a really huge number. That comes out because the electron is exhibiting its wave-like nature. For a dust particle, this was 5 times 10 to the 5 times 10 to the minus 15th. Way smaller. So when it says 6 hours to travel the width of one atom, that's completely different than an electron. This wave-like behavior you would not see. With an electron, you would. So the quantum view has profound implications on the atomic scale, but need not affect the way we think about our macroscopic objects. So this is going on in on the atomic scale. In our everyday lives, we don't see this. So here's some applications and implications of quantum theory. So take a look, through that section. There's nothing on the homework or anything about it, but take a look through this. Maybe you've heard of things like quantum computing, scanning, tunneling microscopes, and things like that. There's a lot of neat technology really that hasn't been completely developed yet. Scanning, tunneling microscope, yes, but quantum computing, it's something that's undergoing current research. So all this neat stuff happens. Okay, so the rest of the slides are just a summary of this chapter. So hopefully you like it. I mean, I remember taking in grad school physics 660, 661, quantum mechanics, all this elaborate mathematics goes along with it. Again, we're at the point where we can describe what's going on, but the why we still don't know. Okay, talk to you